So this video is just a continuation on our Zeeman effect. So continue with our Stern-Gerlach experiment. Remember, we had two magnets here, a plus and a minus right here, or north and south, and we fashioned them so that it gave you a non-uniform magnetic field, a change in B with respect to Z. This is the Z direction, it pinches it right there. But they made the change in magnetic field constant. And so we just showed on the last one that there's a force in the Z direction given by this. Well, this is constant, 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 but you have m sub L right there. And m sub L only has discrete values, which means that the forces, the Z component of the force, are discrete. And that's what they were looking for, these discrete angular momentum components. And what they'd expect to see is, well, in the L equals 0 state, m sub L is only 0, you shouldn't be deflected at all. And if it starts here at a flat beam, it should stay flat. For L equal to 1, the P state, m sub L can be 1, 0, or minus 1, which means it can be deflected up or not be deflected, or be deflected down by this amount. Or if L equals 2, the D state, it could be in 5. So they'd expected to see 2L plus 1 lines right here. And I showed at the end what they saw was just 2 lines. So if this is their drawing right here, they just got 2 lines right here. So what did that mean right here? Well, that told them that maybe there's another type of angular momentum, a whole nother type of angular momentum. Remember, this angular momentum is due to the orbiting electron. Or maybe just like the Earth orbits the sun, but it also spins. So they said, well, maybe the electron has another angular momentum called just due to its spinning right here. And I don't want to call it L because I'll get it confused with the other angular momentum, so we're going to call it S for the spin angular momentum right here. And first of all, what did we say? We had this rule for when you're orbiting. So I would imagine for the spinning right here, instead of an L, you'd have an S. You would have mu sub S right here, and that would depend on minus G sub S. Mu B S. Remember, this is just an angular momentum, but I don't want to get it confused with L divided by H bar. Okay, so just like this one, we got that one over there. And we also said before, actually I'm going to change this a little bit before. I'm going to say what we had for L and then what we're going to do for S. So for L, I'm just going to rewrite what I just had. Mu L equals minus G sub L mu B L all over H bar. But now we're going to have something that's mu S, a magnetic dump due to the spinning electron. Whether it actually spins or not is irrelevant. Minus G sub S mu B S all over H bar. Okay, and we also had our orbital angular momentum defined was the square root of L times L plus 1 H bar. Well, it must mean that we also have our S must be the square root of S, little s, times S plus 1 H bar. Well, here we said the number of lines is 2L plus 1. If you're at here, the number of lines equals 2L plus 1. Well, over here, the number of lines should be 2S plus 1. Well, we know how many lines there is. There's only 2 right here, so it's just 2. So I know what S is, little s. Subtract that right here. It looks like S is just 1/2. That's all it can be, 1/2 right here. We don't even call it a quantum number because it's just one number. It never can be any different, which means that this is equal to the square root of 1/2 times 3/2. 1/2 times 3/2 is 3/4 right here, h bar, or the square root 3/2 h bar. Well, that is what the total spin angular momentum of the electron is. Well, over here we had L sub z, and that was m sub L h bar. Well, if we're going to do that, this has got to be the same, S sub z. Well, that's just going to be m sub s h bar. Well, what could m sub L go from? M sub L, the lowest it can be is minus L, and then you add 1 to it, minus L plus 1, minus L plus 2, all the way up to plus L. It goes from minus L to plus L. Well, what does m sub s do? Same thing. It starts from minus S and it goes all the way to plus S in steps of 1. Well, it goes from minus 1/2 all the way up, and then keep adding 1 until you get to 1/2. Well, that's only gives you, minus 1/2 goes all the way to 1/2. It only has two values, minus 1/2 and plus 1/2 right here. So this is actually what we were using before when we were doing our ups and downs. When we measured S sub z, we got either 1/2 h bar or we got minus 1/2 h bar. So this was really what we're going all the way back to what we did at the very beginning, where we were going our ups and downs. Matter of fact, when you throw this beam in there, anything that came over to here into that beam was my up. This was my up pile. Anything that went over to here was my down pile. If I rotate this thing 90 degrees, I get the two beams like this, and I could get the right pile and the left pile. I could turn it, so you could, this is how, when we had our machine, and we had an arrow, and we had a little digital display, that was it. That's this experiment right here. So this is how we can divide our ups and downs and rights and lefts. You could maybe even use some of this in a quantum computer right here. Oh, okay, so now you wonder why didn't they see these other lines right here? Well, I don't know if it was sheer luck, but if you look up here for silver, right there, silver, you notice that last thing right there, this 4D10 5S1. Well, the 4D10, that's completely filled. So all this, everything below was canceled out. All that momentum canceled out. The only thing I have left is the 5S1. Well, the S state is the L equals 0 state right here. So that didn't do anything to it right here. It didn't deflect it at all. The only thing that is going to deflect it is maybe this term right here, this mu s right here. So, well, now you might say, what is this G sub s right here? So what is G sub s? Well, Dirac derived G sub s when Dirac combined quantum mechanics with relativity. Spin was a natural outcome. It came out of it right here, the whole spin. It doesn't come out of normal quantum mechanics right here, but it comes out when you bring in relativity. And so Dirac, he got G sub s equal to exactly 2 right here. So now, remember, we said this factor of G is somehow related to how the mass and charge are distributed. So let me just do an example right here. Let's just say we have an electron that's in the shape of a cylinder. So we have an electron that looks like this. It's in the shape of a cylinder. You give it some shape right here. And it has some radius r, and it has the mass of the electron. It's in this solid cylinder. But let's just say all the charge is on the surface. So the charge of this charge right here is on the surface. Charge E is on surface, the surface. Okay, and it's going around right here. Okay. So first of all, if I wanted to get the angular momentum, S, I'm not going to worry about the direction of it right here. So maybe I'll just call it without the vector right here. What is the S for this? What is the angular momentum? Well, from classical mechanics, we know it's I omega. S equals I omega, where I is the moment of inertia. We know the moment of inertia of a cylinder is just 1/2 mass of the electron, r squared, mr squared, times omega. So there is what the S is right here. Now mu, since you got charge going around, we can also calculate the mu. Again, it's IA. Well, I is E over the period, like we did before. Area is this area right here, pi r squared. Okay, and actually, I can bring the period up to the top and call it the frequency if I wanted. So we can just make this EF, because since the frequency is 1 over the period, pi r squared. Or I can turn it in terms of omega, because we know that frequency is equal to omega over 2 pi. So let me turn that into an omega over 2 pi. So we get E omega, well, we get the r squared, we get the omega, the pi's would cancel out, and I think we just get a 2. So there's what my magnetic dipole moment is, E omega squared r over 2. Okay, I'm going to take, you noticed here I have an omega r squared, oops, these are the same r's, big r's I guess. I can take the omega r squared and put it down into here. So we end up with mu equals E over 2 times r squared omega. R squared omega is 2s over the mass of the electron. 2s over the mass of the electron. Well, the 2's drop out, so this is the charge of the electron S all over m of the electron right here. But we also have mu from right here. Again, I'm not worried about the sign because I just want to see how the magnitudes compare, but we also got mu sub s from there. It's equal to g sub s mu b s all over h bar. And so if we just equate these two to each other, equate these two, different mu, both mu's right here, plug in what mu b is right here. So we got g sub s. Remember, mu b was EH bar all over 2m of the electron, s all over h bar. Get rid of an h bar. So mu is equal to g sub s E s all over 2m sub e. So just by comparing these two right here, if these two have to be equal, we can see you got an ES over M, so this has got to be 1 So G sub s has got to be 2. So for this shape, G sub s was 2. Now imagine if this were a solid sphere or something other, it would give me a different G right here. Now, this value of G held up for a while right here until quantum electrodynamics was developed right here by Feynman and Schwinger and some other people right here. And what they showed, when you bring in quantum field theory, then this electron also interacts with the vacuum. This magnet right here also interacts with the magnet of the vacuum of space. And so it's slightly different than 2 right here. And this was probably done in the 1940s and in more precise measurements. But right now, G sub s is 2.002, it's pretty close to 2, 3, 1, 9, 3, 0, 4, 3, 6, 2, 5, 6, with an error, plus or minus probably about 35 on the last 2 digits right there. And that's within experimental error. This is when they calculate it and when they experimentally measure it, it comes within that error. This is one of the most precise measurements in all of physics. And you had to again, to get this effect, probably took billions of integrals, maybe even trillions of integrals to do. And because you have to assume every single Feynman diagram, and as you keep making the Feynman diagrams more and more complicated, they become less and less important. And so this is probably, tens of thousands of Feynman diagrams put together, a whole bunch right here. But it's the most precise number in all of physics right here. Now, when you do it for the muon, this was for the electron. Well, the muon, if you do it for the muon with theory, so G, let me put a little mu for the muon right here. It's close to 2. It's 2.00233183620. Doesn't have as many digits right there. If this is theory, and it's like plus or minus 86 out of these last 2 digits right there. But if you look at experimental, G mu experimental, it's 2.0023318. And then right here it's 4121. 82 in these last 2 digits. You'll notice this is a little bit different than that right there. The difference between these two, so far, this has just been done the last year or 2, there is a 4.3 standard deviation difference between these 2 numbers. That means that the odds that this is just a fluke is like 1 in 40,000. Now, I don't know if you've seen in the news over the last month or so, something about a G-2 experiment. It's been hitting the news quite a bit right here, this G-2. Well, what do they mean by G-2 for the muon? They mean this number minus 2. So they don't care about this. They just want to know what all this factor is here. That's why they call it G-2 right here. The reason why is because they did this experiment to get G sub mu a number of years ago. I think it was at least 10 years ago at Brookhaven. And they got like a little bit more than 3 sigma deviation. And so what they did is they took apart the experiment and redid it at Fermilab in Chicago, just outside Chicago. And their results here also pushed it out here, and they've enlarged it to 4.3 standard deviations. Now you might say, what does that mean when these two aren't the same right here? Remember, you got this from theory, from assuming all the Feynman diagrams, so you have to assume that it has these interactions and can make all these particles. Well, it looks like there's some particles that were not taken into account that we haven't discovered yet. So they think maybe there's a possibility that there are new particles right here that haven't been discovered. And you might say, well, how come they haven't had this discrepancy up here? Well, this is much lower mass, and up here you're going to get more higher energy particles right here that we just haven't discovered yet. So in the next couple of years, they're going to redo this experiment, because if they can get this to above 5 standard deviations, that's like 1 in a million that it's a fluke, then they're really going to say there's something wrong with the standard model. So if you see something on the internet about G-2 experiment, that's what they're looking at, this G factor right here. Okay, so now, what happens to our spectra now that we have two types of momentum? We have G, this, and we have that. And when we looked at our energy right here, we said it was due to L sub Z, but now it's also going to be due to S sub Z too. It's going to be the sum of these two right here, because there are two factors here. So our delta E will be G sub L mu B B M sub L. That's due to the orbital, plus you've got the other one, plus G sub S mu B B M sub S. So you got both terms right there. And again, we didn't see it with the Stern-Gerlach experiment because L was 0. M sub L was 0. So we only saw that one right there. Okay, well, we already know that this term is 1. This one is 2. And M sub S can only be a half or 1. It can only be 1/2 or minus 1/2. Whereas this can be, it's an integer right here. Well, let me just rewrite that. So delta E is equal to mu B B M sub L plus, well, actually, let's factor out the mu B B. Mu B B, and we got M sub L plus 2 M sub S. So now, if we go back to our n's right here, we had n equal 1, n equals 2, and n equals 3. And then with just orbital angular momentum, we said that this line didn't move because M sub L was 0. This one moved into 3 lines, equally spaced, right there, for the L equal 1, L equals 0, L equals minus 1. This is M sub L. M sub L, M sub L, M sub L. This is M sub L equals 0. And this one gave me 5 equally spaced. 2, 3, 4, 5. This is M sub L equals 2, 1, 0, minus 1, minus 2. So that's just due to orbital motion right here, motion. But now we can also add the spin to it too. So if we add the spin to it, that means we're adding in this right here. And what's the case right here? When you're down here, this term was 0. M sub S is always plus or minus 1/2, plus or minus 1/2 times 2 is just plus or minus 1. So this thing right down here is just going to split it. It's going to split it up by 1 mu BB and down by 1 mu BB. So this thing is going to go up and down right here by mu BB. Okay. Matter of fact, every single one of these is going to be shifted up or down because this can be plus or minus 1/2, so this can be plus or minus 1 mu BB. So this line over here can be shifted back up to the one, back to the same level, or it can come back down to here. This one can be shifted up to that line, or it can be shifted back down to this, even with that one. And then this one can come back down to that one, or it can come up to here. Same with this one. This one, we'll bring it over a little bit further. This one can go up, or it can go down. This one can come down to here, go up to that level. This one can come back down to this level, or it can go back up to this level. This one like that, and then this one like that. Okay. So now we've got quite a few right here. Remember, these are all, this is m sub L equals 0, and this would be m sub S equals 1/2. This would be m sub S equals minus 1/2. This one down here would be m sub L equals minus 1, m sub S equals minus 1/2. This one up, well, there's going to be 2 on top, but this one down here would be m sub L equals 0. And when you went down, it's m sub S equals minus 1/2. This one is made up of 2 of these right here. One of them that went up, which is the m sub L equals minus 1. And m sub S is plus 1/2. And it could have also been m sub L equal 1. M sub S is minus 1/2. And so on. We can keep going all the way up right here. Now, what is the selection rule? We said before that delta m sub L is equal to 0 or plus or minus 1. But that's not, we need to update it. Really, what it should be is the delta of the total m sub L plus m sub S is 0 plus or minus 1. So, if we come over to here, we already said that when we run down this thing, we got 3 lines right here, always just 3. Now when we're over here, if I were to put in the total m sub S, it is, we really care about is the selection rules on the total. The total here would be minus 3/2. The total here is minus 1/2. So you could jump from here to here. You could not jump from here to here because that difference between minus 3/2 and plus 1/2 is 2 right here. So I could make a jump down to here, right there. Now, that's the only one. This one over here, the total is minus 1/2 when you add these 2 up. This is minus 1/2. Well, if I add 1 or 0, this thing can jump to both of them right here. So this one can jump to both right there. This one up here, over here, this is 1/2 when you add these 2 up. Minus 1/2 because minus 1.5. Minus 1/2. Minus 1/2 can go to both of them. So this one can go to both. And this one is also plus 1/2, and that can go to both right here. So this one can actually go to both right here. And then we could work our way up right here. This one right here, the total, this would be 1/2 because m sub S is 1/2 and m sub L is 0. So this one can jump to both. This one up here, this one is 3/2, M total is 3/2. It cannot jump to the bottom one. It can only jump to the top one right here. So what this is going to do is I can have, this one only had 3 lines. If you add up all the distinct lines here, there are 5 lines. I can get 5 right here. Okay, all equally spaced right here. They're all equally spaced. Okay, and so now what do we have? We now have 4 quantum numbers. What are our 4 quantum numbers? We have our psi, which depends on n, l, m sub l, but now it's m sub s. And m sub s can only be plus or minus 1/2 right here. So what did we say that was? That is equal to r, which depends on n and l. That was our radial equation, which was a function of r. Then we had our spherical harmonic, YL m sub l, which depended on the theta and the phi. Okay, but now we have our spin, our ups and downs. So now if we add our ups and downs, let me just write it like this. I don't know what to use right here, but that's depending on the m sub s right here. And we know that if I operate s sub z, acting on that, m sub s, we know what it is. That's what we got for our ups and downs. This would have been m sub s h bar back to this, which is plus or minus, that was our wave function right here. So let's just say, well, we'll work on that. So this right here is a combination of our ups and downs, but I don't have enough space here. And so next time I'll look at this with everything in there. We still have to put the time back in too. But I should say this right here this is what's called the normal Zeeman effect. All these line splittings, the normal Zeeman effect. Normal Zeeman effect. Now, there is another effect called the anomalous Zeeman effect. Zeeman effect. It's kind of a misnomer because usually you'd think the anomalous Zeeman effect is the rare event and this is what normally happens. No, they've got it backwards. This is what normally happens and this is an anomalous really, but I think it's just probably because of the way they figured it out. What's the difference between these two right here? Well, the normal Zeeman effect is they're all equally spaced. You notice here all the lines are equally spaced. So when you see the lines, they're all equally spaced. With the anomalous Zeeman effect, they're not equally spaced right here. That's one difference. Number two, this one up here, I need to put it into a magnetic field. This one I have even if I don't put it in a magnetic field. So with hydrogen right here, even if I take away the external magnetic field, I'm going to get this line splitting right here. And so we're going to have to go into that and say, why do you get this? Now, if I put it in a real strong magnetic field, this guy will dominate right here. So if I put it in a real strong magnetic field, but in general, what you're going to get is you're going to get splitting here even without an external magnetic field. And so we'll also start to talk about that next time. How do you get this anomalous Zeeman effect? So, okay.